Hey there, team. It's your chemistry coach coming at you for video number 3 for our buffers and titrations and common ion effect chapter here. So we looked at the common ion effect in the first 2 videos and the 2 applications for it. Now let's look at buffers in the second section here. And then we're going to stop for chapter 17 for a while and do titrations at a later date. But buffers, we got to know how to deal with these, all right? Which is just kind of you can think of them as an application of the common ion effect, a very useful application. You've probably seen a lot of definitions for buffer, especially if you've been in biochemistry or biology. So I'll just kind of write something simple. So what would a buffer be? It's a system or a mixture, whatever you want to call it, that can resist or minimize any change in the solution acidity represented by the pH, right? So it resists or minimizes a change in pH. It doesn't prevent a change in the pH, but it minimizes it, right? It resists a change in the pH. Upon addition of either an acid or a base, or if you add water and dilute it, which that would be more of a lab-based effect. We're not going to look at that in the lecture part. So we're going to say, hey, I've got this system, right? This solution, this mixture. And if I drip in some drops of, say, a strong acid, imagine if that was pure water, poof, that pH would just plummet, right? If that was a buffer, and we're going to look at what makes up the components of a buffer, and you add some drops of strong acid in there, you'd expect the pH to plummet. It doesn't. It's like, whoa, that's weird. Or if I add a base to that same buffer system, add a couple drops of sodium hydroxide or something, you'd expect the pH to skyrocket and scoot way up above 7. But it doesn't. It's really fascinating, which means there has to be 2 components to a buffer in one system, in one mixture. You have to have an acidic component and you have to have a basic component, because that acidic component needs to neutralize or help neutralize any added base, and the basic component has to help neutralize any added acid. So this buffer system, whether you add acid or base, it minimizes any pH change upon addition of either. So it must be neutralizing them somehow. And this messed with my brain when I was a student. I'm like, how is that possible? How could something be an acid and a base at the same time? Wouldn't they just neutralize each other? So I was very confused about that and it really racked my brain. So let's take a look on the next board on how this functions. It's going to be really have to focus on whether something's a strong species or a weak species. We're going to find out buffers have to consist of a weak species, can't exist with a strong species, because we need the acid and base to coexist, maybe in equilibrium, and not neutralize each other. So let's take a look at the components that make up buffers. Okay, gang, a couple ways we can think about this. Remember, this buffer has to have 2 components, an acidic component and a basic component. That cannot be a strong species. Remember, the stronger the species, the weaker its conjugate. So like a strong acid like hydrochloric acid would ionize 100% extent. So the HCl wouldn't exist anymore. So if I mixed a strong acid with a strong base, they would just neutralize each other to form water and a neutral salt. It doesn't work out. But if I take a weak acid and its conjugate base, they can coexist in equilibrium without neutralizing each other. We'll look on the next board. You could also have a weak base and its conjugate acid coexisting peacefully so in equilibrium. So you can actually have an equilibrium system of an acidic component and a basic component as long as they're weak, and you've got yourself a buffer system. But you want to have about equal amounts. We'll look at buffer capacity and those kinds of things and buffer range in a little bit. But take a look at this. Let's say I take some generic weak acid. Right? That could be acetic acid, hydrofluoric acid, bromous acid, who cares? That'll ionize in water, forming its conjugate base and the hydronium ion. Right? So if I have this weak acid and its conjugate base coexisting in roughly the same amounts in equilibrium, I've got myself a buffer system. Because if I add a base to this, right, the acid will neutralize it. If I add an acid to it, the base will neutralize it. 2 ways you can look at how buffer systems operate. You can look at it using like the common ion effect and Le Chatelier's principle, or you can look at it using stoichiometrical reactions, acid-base neutralization reactions. In effect, you're taking a weak acid and its conjugate base. Typically, it'll be the salt of that, like, the sodium salt or the potassium salt to form that. But the key is you want roughly similar concentrations of those two. Let's take a look at it from a neutralization perspective first, and then we'll look at it from more of a common ion effect, Le Chatelier's effect. If I take this equilibrium system, a generic one, no specific acid, and I got roughly equal amounts, right? So roughly equal amounts. So roughly equal concentrations. You'll see the importance of that later when we do the quantitative aspects. If I add base to this equilibrium system, which is a buffer, let's just treat that base as the hydroxide ion. Let's bring that hydroxide ion in, right? So that hydroxide ion, you've got an acidic component and a basic component, right? So it's a base, it's going to react with the acidic component. And since that's strong, this will go to 100%, 100%, so it's not going to be reversible. So if I add those together, what am I going to get? I'm going to get water. Right? That H plus comes over, plus A minus. So that weak acid component of the buffer takes out the added base, removes it, forming neutral water plus the A minus. So it just forms, so you lose a little bit of this and increase a little bit of that. From the common ion effect or Le Chatelier's principle, really you're adding the OH minus, which is reacting with this, right? So it's just easier to think of it from the neutralization perspective. We're going to need this when we quantitatively look at it. If we have a buffer system, we can calculate its pH, and we'll say, hey, what if we add, 0.5 milliliters of a, 0.027 molar sodium hydroxide solution? You'll have to set up this stoichiometric equation to figure out how much acid is decreased, right? Because you have some original amount of acid. We got to go, well, you're going to use up some of it neutralizing the added base. So the HA will go down, and it will react this direction. The A minus will go up, right? So the concentrations change. You lose a little bit of this, gain a little bit of that. So that ratio of those concentrations alter a little bit. I'm gonna derive a pretty cool equation that allows you to calculate the pH of buffers called the Henderson-Hasselbalch equation. It's very awesome. Let's say we add some strong acid or any acid. Let's represent the acid as the hydronium acid. So that hydronium is added to the exact same buffer system, but the acid's not going to neutralize the acid. The basic portion is going to neutralize the acid. So the A minus, the conjugate base, that weak base, is going to neutralize any added acid. So it's going to take the H plus. Since that's going to be a strong, this is going to go 100%, so you're going to end up getting neutral water again, right? The H rho plus loses its H plus, and then we get HA. So if we add any strong acid to this, right, that's going to react with it, producing this. So this concentration will go down, and we can calculate that stoichiometrically. This concentration will decrease. That concentration will increase a little bit. That will adjust the ratio, which will alter the pH just a little bit. It's a fascinating concept. So let's take a look at the same board with a base. All right. Actually, you know what? I'm going to derive that Henderson-Hasselbalch equation for acids, and then we'll do the whole thing again for bases and show you how that works out. All right, you ready for some algebraic gymnastics, guys? I love deriving equations. It's a lot of fun. Let's take a look. Let's say we've got a buffer of a weak acid and its conjugate base, roughly equivalent amounts. Let's set up the equilibrium expression for this. So we could say Ka would be the concentration of the conjugate base times the hydronium ion over the original acid, right? What I'm going to do is I'm going to separate a few key terms, and you'll see how this pans out. Ultimately, we're interested in the ratio of the concentration of the weak acid to its conjugate base. So I'm going to take that conjugate base and weak acid, I'm going to separate those out. So I'm going to just rewrite this as the hydronium ion concentration times the ratio of the conjugate base over the original weak acid. You see that ratio there? Those are key. Ideally, they're similar to each other, if not exactly the same, like that'll ever happen. But now let's do some tricks with this. I'm going to take the negative log of both sides. Ultimately, I want to solve for the pH, and pH is negative log H3O plus. So if I took the negative log of both sides, can you see where the negative log of the H3O plus is going to give us the pH? That's why I'm taking the negative base 10 log of both sides. So let's do that. Let's say I got the negative log of Ka will be the negative log of this whole term over HA. I need to pause. I have a kitty cat that wants to come in. I'll be right back. There we go. There's my bead. He's my old, I think he's 19. Something like this guy's been with me forever. I love you so much, BG. All right, anyway, got distracted. All right, here we go. So I have played around with this and just did it to both sides. Negative log of both sides. Do you remember the stupid log trick? Log of A times B is log of A plus log of B. Picture the hydronium ion as A and the ratio of these concentrations of B. So I can split those up. The wonders of logarithms! So nice. So nice. Very nice. Very nice. So that will be the negative log of the hydronium ion concentration plus the negative log of this ratio of the concentrations of the two components of my buffer. Oh, do you see it? Do you see it? It's pH, guys. Negative log of the hydronium is pH. Negative log of the Ka is pKa. You take the negative log of it, you P on it, right? Can you see how this is coming to fruition, gang? So that is pKa equals pH, right? That's my pH, yay, minus the log of the conjugate base concentration over the weak acid concentration. Isolate your pH. So let's move this whole log term over. Let's add that to both sides and get the pH on the left-hand side. You ready? So the pH, I'm going to move this over, will be the pKa plus the base 10 log of the conjugate base concentration over the weak acid. Ooh, wasn't that slick? We got that from the equilibrium expression. I wonder who did this. Henderson and Hasselbalch. Oh my gosh. This is the Henderson-Hasselbalch equation, or just the HH equation, because that gets really long. Henderson-Hasselbalch equation. I'll always provide that for you, although I'd love to test you on the derivation of that. But we got this equation. We can do the same thing for buffers of weak bases and its conjugate acid, which we're going to do next. So qualitatively, we're going to look at it in this video, and then quantitatively, we'll look at pH changes when we add acid or base to buffers. But we can use this equation. This is for buffers. All I do is give you a buffer, say here's the concentration of a weak acid, here's the concentration of its conjugate base, usually as a sodium or potassium salt, calculate those values, right? Look up the Ka of your weak acid, and you're done. You got the pH. It's a piece of cake, guys. It's really easy. You just have to look at that. And if we add acid or base to it, you look at the neutralization stoichiometry I showed you in the last board, right? If I add a base, the HA minus goes down, the A minus goes up. So that ratio changes. If I add an acid, the A minus goes down, but the HA goes up, right? And a couple ways you can think about it, right? If you add acid, this will react with it, right? That drops, that goes up. Another way to think of it using common ion, if I add an acid, this goes up and it shifts this direction, right? So this goes down, that goes. There's different ways you can think about it. I just think the easiest way quantitatively is just as neutralization. Let's set this up for weak bases. And then we'll talk about a few concepts of buffers. We'll be done with this video. In the next video, we'll do an actual problem. All right, guys, see if you can do this one on your own. Exactly the same thing that we did with the weak acid and its conjugate base, the HAA minus weak acid conjugate base pair, roughly equal amounts. Let's do it for a weak base with its conjugate acid. And of course, we would add the salt of its conjugate acid, roughly equal amounts. So we'll just treat generically any weak base. We'll just call that B. B for base. It's getting creative. And its conjugate acid is when it picks up the H plus, the proton. So we'll just say whatever B was, and you stick an H and a positive sign on it, right? So the salt of this would be like the chloride salt, the bromide salt, something. That weak base is going to pull an H plus from water, producing the conjugate acid and the OH minus, and it forms an equilibrium system with constant concentrations. If you add the common ion to it, like a chloride salt of its conjugate acid, and add it to try to get the concentrations of those pretty close to each other, right? That base conjugate acid pair, you got yourself a buffer. But this buffer is made up of a weak base, so that buffer will probably have a pH above 7 somewhere. If you use a weak acid as a buffer, it's probably going to have a pH, somewhere below 7. And you can control those pHs by changing the concentrations of these two species here. Right? You have complete control. You can make a buffer of any pH you want. It's pretty sweet. It's quite a bit of calculations, though, to do it. So let's do exactly what we did with the other buffer with the weak acid and its conjugate base. Let's add a base to it as OH minus and see how it can neutralize that to minimize any change in the pH of that buffer system. And then as well adding an acid to it as hydronium ion and see how this buffer system can neutralize that added acid and minimize any change in pH. It's going to blow your mind how well these things minimize changes in pH upon addition of acid or base. It's phenomenal. I didn't appreciate it as a student, but I do as a professor now, how it works out. And when you see the numbers, it's going to be great. All right. And again, a couple ways you can think about it. You can think about it with the common ion effect and Le Chatelier's principle or stoichiometrically. I personally prefer it stoichiometrically with neutralization because you need that method to do it quantitatively. The other one, thinking of it in terms of Le Chatelier's principle, is more qualitative. Let's say we add some base to it, some sodium hydroxide or whatever. Well, look at your system. You've got the weak base. You've got its conjugate acid. If I'm adding a base, the base part ain't going to neutralize it. The acid part's going to neutralize it. So the conjugate acid will neutralize that strong base to 100%. So it's going to donate its H plus over to give us neutral water. Plus that loses H plus. So you get the basic component of the buffer back. So you neutralize one component of the, so the acidic component of the buffer neutralizes the acid, the added base, producing neutral water plus the basic component. So effectively, this goes down and that goes up. Right? If I add a base to it, this goes down and that goes up. Another, like I said, the other way to think about it with the Le Chatelier's principle, if I add base and I'm increasing this, it's going to shift to the left, right? So this goes down and that goes up. But you don't do calculations with it that way, but you could think of it that way. But here's a better way stoichiometrically. So if I have a certain number of moles of this, it will react with a certain, if I add 0.1 moles of the base, 0.1 moles of this will react with it. So this will go down by 0.1 moles. This will go up by 0.1 moles because the 1-to-1 mole ratio. So you can actually calculate the new concentrations of these, plug it into the Henderson-Hasselbalch equation. Boom, you got your pH. Let's say we add some acid to it as hydronium ion. Well, the acidic portion is not going to neutralize added acid. The basic portion is. So the weak base portion of it's going to react with it. And since we're assuming that's a strong acid, this will go to 100%. So that's going to neutralize it. Again, if I add 0.1 moles of acid, 0.1 moles of this base will neutralize it. So this will go down by 0.1. That'll go up by 0.1 because we're going to form it. So this is going to donate its H plus over to give us neutral water plus the acidic portion of the buffer. Man, this is slick, right? So this would go down. This would go up by equivalent amounts. And again, you can think of it using Le Chatelier's principle, that kind of stuff. If I add an acid, this can take it out. It's going to shift to the right. This goes down, that goes up. By equivalent proportions, calculate the new concentrations of B and BH+, plug it into the Henderson-Hasselbalch equation. Snore, snore, snore. You're good to go. Let's set up the Henderson-Hasselbalch equation for a weak base and its conjugate acid buffer. I dare you, I double dog dare you to see if you can come up with the Henderson-Hasselbalch equation for a weak base conjugate acid buffer, exactly like I did for the weak acid and conjugate base. Give it a shot. See how you do and impress yourself with your algebraic gymnastics. All right. Did you challenge yourself and see if you could do it? It's a great skill to have, to be able to do this algebraic manipulation and derive equations and see where they come from. There's a math class called differential equations that you can take. It's the one I took after I took my 3 semesters of calculus, and then I took differential equations after that. And I learned a lot in DiffEQ about where equations come from. A lot of equations I used in chemistry, I learned how they were derived in differential equations. So that was, I took it as an elective. Why? Why? I could have taken anything I want. I took differential equations. But anyway, there's the masochistic nature of a nerd. Here we go. Let's set up the K. Here's my weak base, conjugate acid, roughly equal concentrations. So let's set up my Kb expression. That will be the concentration of the conjugate acid times the hydroxide ion over the original concentration of the base, the weak base, all to the power of 1. Like we did last time, let's separate out. We're interested in the concentration ratio of the conjugate acid to the base. So let's separate this out. So let's put these in parentheses. Let's put the BH plus there, the conjugate acid, over the base, and separate out the OH minus, right on? Separate that out. Remember, if you take the negative log of both sides, we can split these terms. And we're going to get the POH instead of the pH in terms. So let's take the negative log of both sides. So negative log of Kb will be the negative log of this term. You know what I'm going to do? You okay if I rotate these? You'll see it a little better. I'm going to rotate these. I'm going to put the OH minus there, IBH, and the concentration of the conjugate base over the conjugate acid over the weak base. So I got that ratio of the conjugate acid over the weak base concentration. This is the same as log of A times B. So log of A times B is log of A plus log of B. How many times have we done that stupid math trick, right? So this will be your A, the OH minus. This will be your B, the ratio of the concentrations. But let's separate those babies. So the negative log of the base ionization constant you can find on your weak base table will be equal to the negative log of the OH minus. Remember, when you P on something, right, this will be the pKb, this will be the POH. For acids, that was the pKa and the pH. This will be minus the log of the concentration of the conjugate acid over the original base, doing exactly what we did last time. This becomes pKb. So pKb will be equal to POH minus the log of the ratio of the conjugate acid to the weak base. Now we want to isolate like we did before. Let's isolate the POH. So let's move the log of the concentration ratio over to the other side. So and I'm going to flip this over. So POH will be equal to pKb plus the base 10 log of the conjugate acid concentration over the weak base. So there is the Henderson-Hasselbalch equation for a weak base conjugate acid buffer system. So Henderson-Hasselbalch. Pretty slick, right? Too bad you didn't discover this yourself, and you could have named it after yourself. Now, this requires an extra step. We're going to want the pH, correct? We want the pH, so the extra step is the pH would be 14 minus the POH. That's the only thing about base buffers. You have that extra step because you're actually solving for the POH using the Henderson-Hasselbalch equation. So you just subtract that answer from 14.00 and you got the pH. So let's talk just briefly about capacity. I'm not going to write this stuff down. I'm just going to mention it. You can read about it in the textbook. Capacity, buffer capacity, is the amount of acid or base added that a buffer can neutralize and minimize a decrease in pH. But you can overwhelm a buffer, right? If I just keep dumping strong acid into a buffer, sooner or later, you're just going to blow up your buffer. It's toast. You'll overwhelm. Because if I add a strong acid and this is reacting with it, right? Or if I add a strong base and that's reacting with it, what if I only have 0.2 moles of the conjugate acid and I add 0.3 moles of a strong base? I wipe out this component of the buffer and the buffer falls apart. See that? So it's not perfect, it's limited. Ideally, that's why you want roughly equal concentrations of these. This concentration ratio is the key. You want roughly equal concentrations. If this gets too far off, it messes up the ability for the buffer to work. If this concentration ratio gets, over a 10-fold difference, it becomes a problem. So the effective pH range of a weakly basic buffer is right around the ppb, plus or minus 1, right? So you look up the ppb, say that's, a 4 or something like that. The effective range would be between like a 3 to a 5, plus or minus 1. And if it was an acid, it'd be plus or minus 1 around the pKa value of that. So that's the effective buffer range. But the capacity is limited by the moles, or in some cases millimoles, of the conjugate acid and its base, or the base and its conjugate acid. So the higher those concentrations, the higher these concentrations, the higher the capacity of that buffer to neutralize added acid or base. So just a couple terms there: buffer capacity, buffer range. Lots of different ways to prepare buffers in lab. You can take your, say for example, the base, and you can adjust the concentration of the conjugate acid around that, right? So what you can do is you can adjust, start with equal concentrations of these, and then either add the chloride salt of this, or add a little bit, that would increase this, decrease this, and change that ratio, and it will change the overall pH and POH of that buffer. Or you could add something that the base reacts with to lower that, increase that. Anything you can do chemically to adjust this ratio of the two components in that parentheses term changes this logarithm part. So that you can think of it as the POH of the basic buffer is the ppb plus an adjustment factor for the concentration ratio of those two components of the buffer. And if it was an acid, it'd be the pH is the pKa plus the log of this term. So it'd be the pKa is the baseline, and then you can adjust around that by adjusting the concentrations. But look at the way the logarithm works. If these are equal to each other, that's 1, right? What's the log of 1? Oh, 0. So if these concentrations are equal to each other, this whole term drops out. Nice. And the POH would be the ppb. Or if it was an acid, the pH would be the pKa, right? So that's why I call that a baseline. And then you can adjust the pH of the buffer by just adjusting the ratio of the concentrations of those species by either adding a little acid, adding a little base. There's a lot of different fun ways you can adjust the pH of your buffers to maximize the system, like for a fish tank, if you're a fish person. I am not, but we do have a tank full of fish here, and there's a lot of trial and error trying to get that proper so the fish didn't die. Your blood is one gigantic buffer system, slightly basic, a little over 7. So you can mess up with, you can have metabolic issues, respiratory issues, acidosis and alkalosis, right? Your blood becomes a little too acidic or a little too basic, but your blood has a fascinating buffer system to it when you're doing, different things to yourself, and the way the things we do to ourselves is amazing. But your body is quite capable of minimizing the damage we do to ourselves. So we subconsciously, through our buffer systems, minimize the damage we consciously do to ourselves by ingesting things we shouldn't be ingesting, or doing extreme activities, or having some kind of rare metabolic disease. or some respiratory issue, whatever. That gets into a little more biology and physiology than I'd like to go, but this is the basics of it. So we'll look at a quantitative example in the next video. You guys rock! Keep up the good work!